Hello everyone and welcome to a new stream. How are you doing guys? Today we're gonna keep developing our stuff. Wait. No. That's not what we are going to do today. Today we're gonna study and learn more about matrices. Right? Let's see is if anything if everything is alright. Yeah, okay. Now let's go here. The last time, I mean, we we managed to fix some of this stuff here, and this evening we will keep going developing this. I really wanna add some new features and I mean fix and improve the layout, the interface, and everything. And yeah, that will be very exciting. And we managed to to create real time checks to fix this, and that's cool. That's cool. But now let's focus on this part of the day, which is the SL, studying and learning stuff for university. So right now, I mean, yesterday we discovered how to perform additions and multiplications for matrices. We also learned that there is this associativity and distributivity property. So if we go here, uh, we have this part right here. So a plus b, and then multiplied by c is equal to ac plus bc, right? The same thing applies here. Okay, so this is this rule that we should always remember. And there is also associativity, right? Like it doesn't matter the order of operations, but the order of operands matters. We should always remember this. The order of operands uh, matter, but the order of operation, in this case of multiplication, doesn't. And yeah, this also applies for distributivity. Like we can sum them first and then multiply by c, or then we can multiply uh, them and make a sum. It will be equal, right? So now let's talk about the inverse and transpose. What that is. Okay, we learned the fact that matrices are invertible if there is an inverse, right? And it's and we usually use this notation to mark uh, inverse matrices, and they're called invertible, and if the inverse exists it is unique, right? So that's what we learned yesterday, and on the script we tried to test this, and I still don't know what that is, honestly. But we tested this with our metrics library, and it works, like, right? It works. So if we multiply the first matrix by this component, we get the identity matrix multiplied by this factor here, and this factor is 3 times 2. Wait, it's 1 times 4 minus 3 times 2. I don't know if these are the corners or it's a sum of diagonals, but we know that this operation multiplied by the identity matrix is literally the multiplication between this matrix and this matrix, right? And we simply switched the first indexes, and we multiplied the other ones with by minus 1. So yeah, so this is probably I still don't know what that is, but let's see. And if we multiply this with this matrix, we actually get our reverse matrix. And if and only if this 2 1 2 and 2 1, so if and only if this subtraction is not equal to 0. So minus 2 should be the determinant, right? For what I can understand here. So this minus 2 that we found before should be the determinant of the matrix, right? For what I can understand here. Wait, the fuck is this symbol? Wait, is this on the other pages? I don't know what that symbol is, but that's okay. So we have these 2 matrices, and these are the inverse of to each other. And the interesting part is that the multiplication is creates the identity matrix. So if we multiply if we make a dot product A and B, we get the identity matrix. So let's see if that actually works. So let's create 2 more matrices. I will call those C and D, right? Now what should we do is we should assign this matrix. We should set this matrix. So let's do it right now. So we have C and D. We should pass the dimensions. So we have 3 rows and 3 columns. The same thing here. Then we have these other values right here. So we have 6, 7, and 7. The same thing we have this, right? So let's put this -7, -7, 6. Then we have 2, 1, and -1, right? Then we have 4, 5, and -4, like this. So what happens if we print matrix and then we print the multiplication and we pass C and D. Let's see what happens. We should get the identity matrix, right? Let's try to test it out. And look at this. Yes, that's correct. We get the identity matrix. So if we make a dot product with the inverse of the matrix, we get the identity. So that's why we multiply this, right? And these elements should cancel out, right? Let's see. But what is the determinant of a matrix? Like, is it the top right and bottom left corner of a matrix? Like, is this operation that counts only the tip of the corners, or we have other elements? Because right now we have a 2 by 2 element, right? So let's try to perform this operation. So we have 1 times 7 and 1 times 6, right? So what if we have to subtract the first two? So we have to subtract 7 and then 6. So the result should be 1. So 1 should be the determinant, right? So can we find the determinant? Do we have the determinant function? I think so. So let's try to pass the determinant of this matrix, and it should be 1, right? So let's see what we get. I don't know, I'm not sure, but for what I can understand, this should be the determinant of a matrix. Yes, it's 1. So it's really easy to calculate this, right? What if we skip this? Let's skip this. Wait. Where do we get? Furthermore, we can generally use the determinant to check whether a matrix is invertible. So this should be the determinant. This is the determinant, right? Should be not equal to 0. If it is 0, then the matrix is not invertible, right? So let's go. We have this section, right? And then we use this function that. Let's do a quick. Uh, why is this? Wait, why is this part way far than we are? I really don't understand this. Uh, but we can see that the determinant is a simple multiplication and a subtraction. That's what it is. That's interesting. Hold on. Where the fuck did we get? I fucking lost the. Wait. Okay, here we are. So let's try to do the same thing here. And the determinant should have and the determinant for this matrix should have something related to the other determinant, right? Probably it's this operation, but let's check it out. So we have minus 7 times minus 4, and this and the result is 28 minus 28, right? Then we have 6 times 4, and this is 24, and the result will be minus 4, right? So let's see, like they should have something in common. Let's see if that's right. If I did the right calculation. So we go here and we check this. 6. I don't understand why is this orange. What the hell? Why is this? Bro, this is confusing. Okay. Then we have 2, 1, minus 1. 2, 1, minus 1. Then we have 4, 5, minus 4. Let's check that out. For some reason, it's still 1. So it is the same. What? Wait, I think I did something wrong here. So we have minus 7, then we have minus 4. Let me use my calculator. So we have minus 7 times minus 4. Oh, right, this is a positive term. Okay, yeah, this. Okay, that was dumb, but wait, what the fuck? Wait, what is this? Minus 7 times minus 4. That's a positive term. The fuck you mean? Wait, let me just. What the fuck, bro? Let me just do this. Shit. And it is 28 minus 24. It should be 4. I don't know why, but it's not. It's still 1. I don't understand, honestly. What is the determinant? What is exactly? determinant of a matrix. Wait, that's more complicated than I thought. Okay, this is a scalar multiplication and then we have a sum. Okay, that's not that's more complicated than I thought. So we should have something like this and Jesus. This is uh this is a little bit confusing, but that's normal. I just discovered what determinants are. But if we multiply uh, the reverse of the determinant by the matrix, we perform this scalar multiplication, we find the inverse, right? Probably. So then we have this part here. We still have some properties. And the fact is this doesn't apply for the sum. Like the inverse doesn't apply for the sum. It's not equal. But for the multiplication it is. And these are so if we multiply this we find the identity matrix. If we multiply this and then apply the inverse, we get this. It's like the multiplication for each element inverted. Then we have symmetric matrix. A matrix as an element of the set of real numbers of a square matrix, in this case, is symmetric if A is equals to A transpose. Okay. So it's simply a matrix rotated, right? And we also have this property. The sum of symmetric matrices A and B is always symmetric. However, although the product is always defined, it is generically not symmetric. Okay, the sum is always symmetric, but the product is not symmetric. And that's the example. Okay, the sum is symmetric, but the product isn't always symmetric. It's generally not. Then we have this part, uh, the inverse, and then we transpose, or we transpose, and then we have the inverse. It's the same thing. And this is the A and the inverse and transpose of A. Yeah, it's basically the same thing, right? The only difference is the sum is handled differently. Like these are not equal, but these are equal. So the matrix is symmetric if A is equals to A transpose. Of course, only square matrices can be symmetric. Yeah, it can be invertible. Yeah, that of course they can because the determinant kind of remains the same, right? Like I mean, the determinant. I don't know if it changes, but the the determinant is always not equal to zero if the other is not equal to zero, right? Then we have the multiplication by a scalar. And I think this is the simplest form of multiplication, right? By a scalar, lambda, and okay, we have this k, okay, kij, each element of k is equal to each element of a multiplied by lambda. So this is pretty much the same. So also we have this symbol. Is this phi? What is this? This is psi. Oh my god. We still have this associativity. Yeah, that's pretty much obvious. Yeah, we can perform the order doesn't really matter. And how can we transpose a scalar value? Like it's literally the same thing. A transpose, a scalar transpose is just is the transpose itself. Yeah, exactly. Like I I don't think there is much sense writing this, but that's okay. So we should always remember these properties. And yeah, it won't be that easy to remember actually because uh, I don't know. So let's create uh, a new function that, and we will call it scale matrix. So we get the first part, and honestly, does the order of operands matter? It does not. It doesn't. So for what I can see here, the order of these operands does not matter. So we can just create a new argument here. So let's uh, create this, and we get um, scale. I don't know, I will call it scale. Then let's copy the definition. Then we get this. So now the only thing we should do, we should just iterate for each I. So for each I and j. So we simply need one loop, and x dot rows times x dot columns, and we add this, and then we have to assign this. So we get x data, and we should difference this, of course. And this should be x dot data times scale, right? Let's see what happens if we. So let's create this matrix. So we have matrix T AB is equal this, and then let's see what happens if we multiply this. Like, let's see, we have scale matrix, then we have AB, and we scale it by, I don't know, 7. Let's see if that works. Oh my fucking god. I don't think this is supposed to happen. What the hell? Okay. That definitely isn't supposed to happen. Wait, what even am I doing here? Why am I differencing like that? I don't know. I don't know why I was differencing it like this. Also, I didn't return anything. Oh my god, I'm so dumb. I have to create a new result, right? So let's do that. So we have this, we have res, matrix T res is create matrix, and it's a x dot rows and x dot columns. Then we get res is equal this. I will use res because why not? Let's try again. Yeah, and that's basically it. Like we don't need anything else. Um, yeah, this is pretty much how it works. Okay, this book didn't really cover um, inverse and the determinant because it will do that later. Then we have the compact representation of systems of linear equations, and we have something like this. So we have the coefficient multiplied by each x. So this is multiplied by this, then we have this multiplied by this, and this multiplied by this, right? So this is a 3 by 3 and 3 by 1. And we get a 3 by 1 result. Really easy to find everything. Yeah, I agree, like this is pretty much how it works. And then we have 182. So we have to find this like also we I forgot that we also have to sum this, right? Yeah. So this is this and this and this, then we sum it together. I forgot this that the components that we should sum the components. Actually, I forgot that. That's what we have. So yeah, it's pretty much how it works. Note that x1 scales the first column, x2 the second one, and x3 the third one. Yep, yep, that's true. Generally, a system of linear equations can be compactly represented in their matrix form as ax equals b and the product ax is a linear combination of the columns of A. Wait, what is A and what is B? So this is A, X. Oh, okay, this is A, this is X, and this is equals to the B, right? So okay. Okay, we discuss about it later. So now we have solve a system of linear equations, right? Okay. Can we perform this? So the numbers of columns on the first matrix should be equal to the number of columns of the second matrix. And in this case, we can perform this operation. And to find the actual sides of the of the fucking result, we have we consider we have 2 by 4. So um, let me just let me open this. So let's consider that uh, we have this, right? So by following this rule, we should have we have this, and the dot product is by m rows, so we have 4 rows and 1 column. And if we cancel out, we get 2 by 1, 2 rows and 1 column, and that's what we get: 2 rows and 1 column. So to perform this operation, we do this, then we do this part, this part, and this part, then we sum it together, and then we do this part right here, this part right here, this part right here, this part right here, and we sum it together. Pretty much how it works. Let's read this part. Also, I would keep watching this series. So if we search free blue and brown, let's keep watching the series, because this is really interesting, right? So we are starting to get a deep understanding of what we are studying for, of what we are learning. So this at first, free blue one brown treats vectors as arrows. It's the physical perspective, right? The physics perspective. So they think as arrows on a plane, on a 2D plane, or sometimes a 3D plane, right? Now we have to watch this video. So let's watch this video and let's see what we can understand for it. I don't know if I should use wait. I am afraid that if I use the highest quality, my stream crashes. That's my only concern. I'm still streaming, by the way. Yep, I am. Wait, what the hell? Where did the rest of my channel go? Like, everything disappeared. What the hell? So, let's go. Let me just... yeah. Let me just listen to his...
everyone, where we last left off, I showed what linear transformations look like and how to represent them using matrices. This is worth a quick recap because it's just really important. But of course, if this feels like more than just a recap, go back and watch the full video. Technically speaking, linear transformations are functions with
Yeah,
vectors as inputs and vectors as outputs. But I showed last time how we can think about them visually as smooshing around space in such a way that grid lines stay parallel and evenly spaced, and so that the origin remains fixed. A
exactly.
key
Yeah,
takeaway was that a linear
the
transformation
basis
is
vectors.
completely
Right.
determined by where it takes the basis vectors of the space, which for
Exactly.
two dimensions means I hat and j hat.
So we just have to multiply the old position by the new position of the basis vectors, and we find the new position of the points.
This is because any other vector could be described as a linear combination of those basis vectors. A vector with coordinates x, y is x times I hat plus y times j hat. After going through the transformation, this property that grid lines remain parallel and evenly spaced has a wonderful consequence. The place where your vector lands will be x times the transformed version of I hat plus y times the transformed version of j hat. This means if you keep a record of the coordinates where I hat lands and the coordinates where j hat lands, you can compute that a vector which starts at xy must land on x times the new coordinates of I hat plus y times the new coordinates of j hat.
Yeah,
The
exactly. Yeah.
convention is to record the coordinates of where I hat and j hat land as the columns of a matrix, and to define this sum of the scaled versions of those columns by x and y to be matrix vector multiplication.
Okay, what the hell is this? Okay, yeah.
In this way, a matrix represents a specific linear transformation, and multiplying a matrix by a vector is what it means computationally to
Wait, let me just.
multiplication.
So we. So yeah, this is pretty much what we do. So we take a um then we sum it, right? Oh yeah. So we take x and then we have by and we sum it like that. And actually it's equal to do something like this. That makes sense. That makes sense. Yeah. And that's the new position, of course.
In this way, a matrix represents a specific linear transformation, and multiplying a matrix by a vector is what it means computationally to apply that transformation to that vector. Alright, recap over. On to the new stuff. Oftentimes, you find yourself wanting to describe the effects of applying one transformation and then another. For example, maybe you want to describe what happens when you first rotate the plane 90 degrees counterclockwise, then apply a shear. The overall effect here, from start to finish, is another linear transformation, distinct from the rotation and the shear. This new linear transformation is commonly called the composition of the two separate transformations we applied. And like
Oh yeah, the composition is when we like when we pass a function into another function, right?
any linear transformation, it can be described with a matrix all of its own by following I hat and j hat. In this example, the ultimate landing spot for I hat after both transformations is 1, 1. So let's make that the first column of a matrix. Likewise, j hat ultimately ends up at the location negative 1, 0. So we make that the second column of the matrix. This new matrix captures the overall effect of applying a rotation then a shear, but as one single action rather than two successive ones. Here's one way to think about that new matrix. If you were to take some vector and pump it through the rotation, then the shear, the long way to compute where it ends up is to first multiply it on the left by the rotation matrix. Then take whatever you get and multiply that on the left by the shear matrix.
Okay. That's also equals to the distributivity property. or associativity. Wait, which one was it? I fucking forgot. But if we do the shear first, then we apply the rotation right here. It should be the same, right? Let me check the properties right here. So we have, yes, it should be like this, right? So let's keep going. So we can also switch the sides.
This is, numerically speaking, what it means to apply a rotation, then a shear, to a given vector. But whatever you get should be the same as just applying this new composition matrix that we just found by that same vector. Nope.
Let me just check. So we have 1 times 0. It's just 0. That's why we still have 0 right here. Wait, what do you mean? Wait. So what if that we have, hold on. Oh, this is 1. Okay, the first term is 1. I don't know why I multiply for this term here, but so we have 0 plus 1, and we have 1. Then we have 1 minus 1, and then 0, and we have minus 1, right? Yeah. Then we have 0 and 0 plus 1 by 1, and it is 1. Then we have 0 and 0, wait, 0 and minus 1, which is 0, and then we have 1 and 0, which is 0. So yeah, everything is correct. Yeah.
No matter what vector you chose, since this new matrix is supposed to capture the same overall effect as the rotation then shear action. Based on how things are written down here, I think it's reasonable to call this new matrix the product of the original two matrices.
Yeah, exactly. This is the
We can
dots
think about how
product.
to compute that product more generally in just a moment, but it's way too easy to get lost in the forest of numbers. Always remember that multiplying two matrices like this has the geometric meaning of applying one transformation, then another.
That's cool.
One thing that's kind of weird here is that this has us reading from right to left. You first apply the transformation represented by the matrix on the right, then you apply the transformation represented by the matrix on the left. This stems from
Yeah.
function notation, since we write functions on the left of variables, so every time you compose two functions, you always have to read it right to left.
Oh, that's true. Yeah. It's like the, yeah.
Good news for the Hebrew readers, bad news for the rest of us. Let's look at another example. Take the matrix with columns 1, 1 and negative 2, 0, whose transformation looks like this. And let's call it M1. Next, take the matrix with columns 0, 1 and 2, 0, whose transformation looks like this.
Oh,
And let's
Jesus.
call that guy M2. The total effect of applying M1, then M2, gives us a new transformation. So let's find its matrix. Put this
Okay, there should be. Yeah, hold on. Let me just try to calculate this by myself. So we have 0 and 1. Then we put this 0. Then we have 2 and 1. Then we have 2. Then we have 1 and 1 here, and this is 1. And we have 0 and 1, and this is, oh god, I got confused. Well, hold on. So we have 0 plus 2, and this is 2. Then we have 0, so we have 2, 0. Then we have 1, 1, 1, 1, and wait, 1, 1 and 0, 1. And this is 1, so we have 2, 0 and 1. Then we have 2, 1 minus 2, and then we have 0. So it should be 2, 1, minus 1, and minus 2, right?
This time, let's see if we can do it without watching the animations, and instead just using the numerical entries in each matrix. First, we need to figure out where I hat goes. After applying M1, the new coordinates of I hat, by definition, are given by that first column of M1, namely 1, 1.
Oh,
To see what happens after applying M2, multiply the matrix for M2 by that vector, 1, 1. Working it out the way that I described last video, you'll get the vector 2, 1. This will be the first column of the composition matrix. Likewise, to follow J hat, the second column of M1 tells us that it first lands on -2, 0. Then, when we apply M2 to that vector, you can work out the matrix vector product to get 0, -2.
now this is another way to think about it. And it's pretty cool. Wow, yeah, I have to get used to think about this. So we just have, like, we can think about the sum of the scalar values. One represents the coordinates of I, and the other one represents the coordinates of J hat, of course.
which becomes the second column of our composition matrix. Let me talk through that same process again, but this time I'll show variable entries in each matrix, just to show that the same line of reasoning works for any matrices.
So we have this component multiplied by this plus this component multiplied by this, and then we have uh, this component multiplied by this plus this component multiplied by this.
This is more symbol heavy and will require some more room, but it should be pretty satisfying for anyone who has previously been taught matrix multiplication the more rote way. To follow where I hat goes, start by looking at the first column of the matrix on the right, since this is where I hat initially lands. Multiplying that column by the matrix on the left is how you can tell where the intermediate version of I hat ends up after applying the second transformation. So the first column of the composition matrix will always equal the left matrix times the first column of the right matrix.
Wait. Yeah, that's exactly, yeah.
Likewise, J hat will always initially land on the second column of the right matrix. So multiplying the left matrix by this second column will give its final location, and hence that's the second column of the composition matrix. Notice, there's a lot of symbols here, and it's common to be taught this formula as something to memorize, along with a certain algorithmic process to kind of help remember it. But I really do think that before memorizing that process, you should get in the habit of thinking about what matrix multiplication really represents, applying one transformation after another. Trust me, this will give you a much better conceptual framework that makes the properties of matrix multiplication much easier to understand.
Oh, yeah. So it's like, so let me think about this one. So I fucking need space. Fuck off, new file. So a matrix is a transformation, right? So we have um, I don't know, we have some values, right? We have A, B, C, and D, and then we have I call it the positions, right? Of I, X, I hat X, and I hat Y. Then we have J at X and J hat y, right? Now we simply apply the multiplication for um, so we have, let me just try to think about this. So we have A and C, right? Plus um, B and D. I'm not sure, but I think for what I understand, like then we find the first column of the results, right? Let me just try to think about this. So we have, yeah, it's pretty much how it works. So we have this transformation, right? And we have the other one. So this is y, and this is j, right? Wait, what am I doing? Can we store this inside you know, a large vector? Not sure, but I'll try this. So now let's get this, and we should do the same thing for this terms, right? Plus j hat, and then we have b and d. This is pretty much how it works, right? So we have this part here, and then we have this part right here. So let's align this. Let's use colors because I think colors are more intuitive, and the brain can process colors way better. So yeah, by the way, this is also the purpose of syntax highlighting. That's why codes that's why code is colorful.
And it's common to be taught this formula as something to memorize, along with a certain algorithmic process to kind of help remember it. But I really do think that before memorizing that process, you should get in the habit of thinking about what matrix multiplication really represents, applying one transformation after another. Trust me, this will give you a much better conceptual framework that makes the properties of matrix multiplication much easier to understand. For example, here's a question. Does it matter what order we put the two matrices in when we multiply them? Well, let's think through a simple example, like the one from earlier. Take a shear, which fixes I hat and smushes j hat over to the right, and a 90-degree rotation. If you first do the shear, then rotate, we can see that I hat ends up at 0, 1, and j hat ends up at negative 1, 1. Both are
Yeah,
generally pointing close together. If you first rotate, then do the shear,
it's not the
I
same.
hat ends up over at 1, 1, and j hat is off in a different direction at negative 1, 0, and they're pointing, farther apart. The overall effect here is clearly different, so evidently order totally does matter. Notice, by thinking in terms of transformations, that's the kind of thing that you can do in your head by visualizing. No matrix multiplication necessary. I remember when I first took linear algebra, there was this one homework problem that asked us to prove that matrix multiplication is associative. This means that if you have three matrices, A, B, and C, and you multiply them all together, it shouldn't matter if you first compute a times b, then multiply the result by c, or if you first multiply b times c, then multiply that result by a on the left. In other words, it doesn't matter where you put the parentheses. Now, if you try to work through this numerically, like I did back then, it's horrible, just horrible, and unenlightening for that matter. But when you think about matrix multiplication as applying one transformation after another, this property is just trivial. Can you see why? What it's saying is that if you first apply C then B, then A, it's the same as applying C, then B, then A. I mean, there's nothing to prove. You're just applying the same three things one after the other, all in the same order. This might feel like cheating, but it's not. This is an honest-to-goodness proof that matrix multiplication is associative. And even better than that, it's a good explanation for why that property should be true. I really do encourage you to play around more with this idea, imagining two different transformations, thinking about what happens when you apply one after the other, and then working out the matrix product numerically. Trust me, this is the kind of playtime that really makes the idea sink in. In the next video, I'll start talking about extending these ideas beyond just two dimensions. See you then!
So yeah, that's pretty interesting, right? So if we apply this, um, honestly, I don't know how to represent this numerically. So that's the fucking graph, right? Let me just create squares just to, you know. So what we did here, right, like we probably multiplied this value, right? So this is I hat and this is j hat, right? And this is quite confusing actually. I mean, we have this and this. Like, what transformation do we have here? Okay. Trying to focus on how this works. Like, I mean, graphically. So each multiplication, it's multiplication, oh my fucking god, each dot product is a transformation of this graph, right? So when we move this, we actually applied the transformation. we applied a product, right? So we should store this. For what I can understand, like we should store the. Uh, this is the original positions, right? This is the original position. Then we should probably store the new position, right? Then we have we have 1 and 0. Then we have uh, j, which is 1 and 1, right? Oh god. So what if we have a line here, and then by applying this line ends up um, probably here, right? Let's see, we should multiply this by 1 and 1, right? The new vector gives us the position of the new like gives the values of the new positions, right? So it should be 2 1, right? Let's check if that's true. So we have let's do this. Let's do the dot product. We have 1 and 1, then 1 and 1 we sum it, and then we get 2. Then we have 0 and 1, which is 0 plus 1 times 1, which is 1. And holy fuck. Okay. That's interesting. Wow. So we can think about this is the shear, right? Right? So we apply the shear, and we like what 3b1b told us to do, we did it, and actually it's really simple to imagine this. So what if, let me try to draw a graph. I don't know, I'm trying to create. So we have this. Let me just copy this and paste this and another. Okay. So let's duplicate this so we can keep track of y and j. Honestly, I don't really know. Let's create. So let's apply another transformation, right? And this time we will use y marked as red and j marked as blue, or the opposite thing, right? So right now we have let's try to apply. Okay, we still have this, right? Then we have the point, and let's pretend we are still here, right? Or I will draw this here. And let's pretend that we have a new transformation, which is I don't know. I don't know. I'm trying to. I think I'm stupid because I'm trying to overcomplicate things, right? So we have the transformation. Okay, this is the transformation. We should keep record of the transformation. Then we have the new positions of uh, I hat. So it is uh, 0 and 1. Then we have 2 and 1, right? Then we should multiply this by the position of this position. So we have -1 and then 1, right? That's basically how it works. Like it should work, right? So let's try to apply this multiplication. Let's try to make the dot product. So we get, let's see, for the first column, we actually get, so we have 0 minus 1, which is 0, plus 2, so we get 2 here. Then we have 1 and -1, which is -1, plus 1, which is 0, right? So we have 2 and 0, and it should be here. I don't know if that's accurate, but what if, like, uh, we definitely, okay, what happened here is that we rotated this, right? Or actually we flipped this. So we flipped this. So we flip I, right? And then we stretched J, right? So this will be here, right? And then we kind of applied this rotation. So wait, this should be here. This should be here. Probably. Wait. Yeah. Oh my fucking god, can you? And since we are rotating this, are we actually rotating it? Oh my god, why am I obsessed to make other complicated examples? This is actually a composition, right? This is a composition of flipping it over and then shearing, right? So we have to divide this into two transformations, right? Probably. And I kinda get the point. But I just overcomplicated myself for nothing. I don't know. So let's go here. And holy fuck, we need to. What if we apply this transformation, right? Um, nope, I'm not gonna do that. I'm not going to do that. I'm not gonna do that. I just know that the result should be here. So let's think of this plane, right? And this will be reversed, right? So if we flip y and j, hold on. Let me just put this on this perspective. So we don't actually need to flip this. It's supposed to be here. Why the fuck did I put this there? So, and then we put this here, right? Uh, and this should land uh, so if flip everything, this should land here, right? Then if we move this here, right? Like this should be at the origin, right? Like this. And then if we finally stretch this, we also stretch this part. And that's where it basically goes, right? Okay. I don't know why I like to overcomplicate things, but yeah, I think I get the point. Okay, I streamed for 1 hour and a half. I'm gonna take a break, so I'll be right back. So we also have the determinant. Wow, that's cool. I'm not. I don't think I'm ready for 3D transformations. Honestly, I have to. I still have to digest this info, right? Because we can't think of a transformation, right? How the graphs actually transforms. I'm gonna take a shot break. So uh, I'll be right back. Okay, I'm back. I took a break. Yeah. So that's basically how it works. Like it's just a transformation, right? Now we have to think about 3D matrices. Okay, and I think we are gonna, you know, are gonna get 3 by 3 matrices or anything like that, right? Oh my gosh. So let's keep going with the video.
Hey folks, I've got a relatively quick video for you today, just sort of a footnote between chapters. In the last two videos, I talked about linear transformations and matrices, but I only showed the specific case of transformations that take two-dimensional vectors to other two-dimensional vectors. In general throughout this series, we'll work mainly in 2 dimensions, mostly because it's easier to actually see on the screen and wrap your mind around. But more importantly than that, once you get all the core ideas in 2 dimensions, they carry over pretty seamlessly to higher dimensions. Never.
I think I should create a simulation that simulates this graph, right? We will do this. We will do this. We can do everything we want.
Nevertheless, it's good to peek our heads outside of Flatland now and then to, see what it means to apply these ideas in more than just those 2 dimensions. For example, consider a linear transformation with 3-dimensional vectors as inputs and 3-dimensional vectors as outputs. We can visualize this by smushing around all the points in 3-dimensional space, as represented by a grid, in such a way that keeps the grid lines parallel and evenly spaced, and which fixes the origin in place. And just as with 2 dimensions, every point of space that we see moving around is really just a proxy for a vector who has its tip at that point. And what we're really doing is thinking about input vectors moving over to their corresponding outputs. And just as with 2 dimensions, one of these transformations is completely described by where the basis vectors go. But now...
Oh, now I understand how some engines calculate the rotation using matrices. I mean, rotation and moving parts, right? Uh, but they actually use quaternions, and we are gonna learn this later, right?
Now, there
And
are
now
3
let's
standard
focus on
basis vectors
matrices.
that we typically use. The unit vector in the x direction, I hat, the unit vector in the y direction, j hat, and a new guy, the unit
K.
vector in the z direction, called k hat. In fact, I think it's easier to think about these transformations by only following those basis vectors, since the full 3D grid representing all points can get kind of messy. By leaving a copy of the original axes in the background, we can think about the coordinates of where each of these 3 basis vectors lands. Record the coordinates of these 3 vectors as the columns of a 3x3 matrix.
Oh, okay. It's kind of the same thing that we did here. Like, yeah.
This gives a matrix that completely describes the transformation using only 9 numbers. As a simple example, consider the transformation that rotates space 90 degrees around the y-axis. So that would mean that it takes I hat to the coordinates 0, 0, -1 on the z-axis. It doesn't move j hat, so it stays at the coordinates 0, 1, 0. And then k hat moves over to the x-axis at 1, 0, 0. Those 3 sets of coordinates become the columns of a matrix that describes that rotation transformation. To see where a vector with coordinates x, y, z lands, the reasoning is almost identical to what it was for 2 dimensions. Each of those coordinates can be thought of as instructions for how to scale each basis vector so that they add together to get your vector. And the important part, just like the 2D case, is that this scaling and adding process works both before and after the transformation.
So we apply the same concept that like we multiply. I mean, yeah, we multiply this by the basis, and then we get the new vector, right? So we have a vector, and then we have to multiply this by the basis, like individual basis, and then we get the new position, right?
to get your vector. And the important part, just like the 2D case, is that this scaling and adding process works both before and after the transformation. So to see where your vector lands, you multiply those coordinates by the corresponding columns of the matrix, and then you add together the three results.
Yeah. Okay, yes. So let's.
Multiplying two matrices is also similar. Whenever you see two 3x3 matrices getting multiplied together, you should imagine first applying the transformation encoded by the right one, then applying the transformation encoded by the left one. It turns out that 3D matrix multiplication is actually pretty important for fields like computer graphics and robotics, since things like rotations in 3 dimensions can be pretty hard to describe, but they're easier to wrap your mind around if you can break them down as the composition of separate, easier to think about rotations.
That would be useful when we do OpenGL stuff, right?
Performing this matrix multiplication numerically is, once again, pretty similar to the two-dimensional case. In fact, a good way to test your understanding of the last video would be to try to reason through what specifically this matrix multiplication should look like, thinking closely about how it relates to the idea of applying two successive transformations in space.
So yeah, we can apply this. We can use the composition, right? We can multiply this together, and we will get the composition of the two transformation, and then we multiply this by the respective coordinates. So to find the new coordinates which the new vector is pointing to, right?
In the next video, I'll start getting into the determinant.
Okay, the next video should be interesting, right? So let's get into the sixth part of this series.
Hello again. So moving forward, I'll be assuming that you have a visual understanding of linear transformations and how they're represented with matrices, the way that I've been talking about in the last few videos. If you think about a couple of these linear transformations, you might notice how some of them seem to stretch space out, while others squish it on in.
Yes.
One thing that turns out to be pretty useful for understanding one of these transformations is to measure exactly how much it stretches or squishes things. More specifically, to measure the factor by which the area of a given region increases or decreases.
Well, is that the
For
determinant?
example, look at the matrix with columns 3, 0, and 0, 2. It scales I hat by a factor of 3 and scales j hat by a factor of 2. Now, if we focus our attention on the 1 by 1 square whose bottom
Wait.
For example, look at the matrix with columns 3, 0, and 0, 2.
Yes.
It scales I hat by a factor of 3 and scales j hat by a factor of 2. Now, if we focus our attention on the 1 by 1 square whose bottom sits on I hat and whose left side sits on j hat, after the transformation, this turns into a 2 by 3 rectangle. Since this region started out with area 1 and ended up with area 6, we can say the linear transformation has scaled its area by a factor of 6. Compare that to a shear, whose matrix has columns 1, 0, and 1, 1.
The area doesn't change.
Stays in place, and j hat moves over to 1, 1. That same unit square, determined by I hat and j hat, gets slanted and turned into a parallelogram. But the area of that parallelogram is still 1, since its base and height each continue to have length 1. So even though this transformation smushes things about, it seems to leave areas unchanged, at least in the case of that one unit square. Actually though, If you know how much the area of that one single unit square changes, it can tell you how the area of any possible region in space changes. For starters, notice that whatever happens to one square in the grid has to happen to any other square in the grid, no matter the size.
Yeah, that's
This
true.
follows from the fact that grid lines remain parallel and evenly spaced. Then, any shape that's not a grid square can be approximated by grid squares pretty well, with arbitrarily good approximations if you use small enough grid squares. So, since the areas of all those tiny grid squares are being scaled by some single amount, the area of the blob as a whole will also be
Multiplied
scaled
by
by that
the,
same single
yeah.
amount. This very special scaling factor, the factor by which a linear transformation changes any area, is called the determinant of that transformation.
Wow.
I'll show how to compute the determinant of a transformation using its matrix later on in this video, but understanding what it represents is, trust me, much more important than the computation.
Oh, that's cool. I didn't know that. Of course, I didn't know. I'm here to learn things, but this is insane. Like, they didn't told me on my university. Like, they didn't tell me this. They didn't tell me this. That's that's actually a cool thing. So it's the change of the area, right?
For example, the determinant of a transformation would be 3 if that transformation increases the area of a region by a factor of 3. The determinant of a transformation would be 1/2 if it squishes down all areas by a factor of 1/2. And the determinant of a 2D transformation is 0 if it squishes all of space onto a line, or even onto a single point, since then the area of any region would become 0.
And the matrix wouldn't be invertible, right?
That last example will prove to be pretty important. It means that checking if the determinant of a given matrix is 0 will give a way of computing whether or not the transformation associated with that matrix squishes everything into a smaller dimension. You'll see in the next few videos why this is even a useful thing to think about, but for now I just want to lay down all of the visual intuition, which in and of itself is a beautiful thing to think about. Okay, I need to confess that what I've said so far is not quite right. The full concept of the determinant allows for negative values. But what would...
Wait, if if it does that mean if we we flipped if we flip the square, right? If we flip the square, we get a negative determinant, right?
the idea of scaling an area by a negative amount even mean? This has to do with the idea of orientation. For example, notice how this transformation gives the sensation of flipping space over.
Oh my god,
If you were
yes.
thinking of 2D space as a sheet of paper, a transformation like that one seems to turn over that sheet onto the other side. Any transformations that do this are said to invert the orientation of space. Another way to
Yeah,
think about it is in terms of I hat and J hat. Notice that
so yeah, exactly what I say. Like, in this case, the determinant of this transformation matrix should be negative, right? So, uh, this looks. Oh god. How can I? What's the symbol? I cannot do this symbol, but so this is the symbol. This should be less than 0, right?
their starting positions, J hat is to the left of I hat. If, after a transformation, J hat is now on the right of I hat, the orientation of space has been inverted. Whenever this happens, whenever the orientation of space
Wait, inverted? Wait. This reminds me of the inverted matrix, right? Wait. There is actually a connection, right? Oh my god, what the fuck is happening? Let me just close some tabs here, and I'm gonna probably close this one. Yeah. So as we like, if we find this, where is it? It's right here. So if this is 0, we can invert it because it squishes down everything. It squishes everything, right? But if we have a determinant of a 2 by 2 matrix, we can actually check, we can actually tell if this matrix is invertible, right? Where is it? There it is. And when it's invertible, do they mean something
Is inverted.
like inverting this, this space, this 2D space, or the space in general?
Inverted. Whenever this happens, whenever the orientation of space is inverted, the determinant will be negative. The absolute value of the determinant, though, still tells you the factor by which areas have been scaled. For example, the matrix with columns 1, 1, and 2, negative 1 encodes a transformation that has determinant, I'll just tell you, negative 3. And what this means is that space gets flipped over and areas are scaled by a factor of 3. So why would this idea of a negative area scaling factor be a natural way to describe orientation flipping? Think about the series of transformations you get by slowly letting I hat get closer and closer to J hat. As I hat gets closer, all of the areas in space are getting squished more and more, meaning the determinant approaches 0. Once I hat lines up perfectly with J hat, the determinant is 0. Then, if I hat continues the way that it was going, doesn't it kind of feel natural for the determinant to keep decreasing into the negative numbers?
Yeah.
So that's the understanding of determinants in 2 dimensions. What do you think it should mean for 3 dimensions? It also tells you how much a transformation scales things, but this time, it tells you how much volumes get scaled. Just as in 2 dimensions, where this is easiest to think about by focusing on one particular square with an area 1 and watching only what happens to it, in 3 dimensions, it helps to focus your attention on the specific 1 by 1 by 1 cube whose edges are resting on the basis vectors, I hat, j hat, and k hat. After the transformation, that cube might get warped into some kind of slanty cube. This shape, by the way, has the best name ever, parallelepiped, a name that's made even more delightful when your professor has a nice thick Russian accent. Since this cube starts out with a volume of 1, and the
parallelepiped, what?
Nice thick Russian accent. Since this cube starts out with a volume of 1, and the determinant gives the factor by which any volume is scaled, you can think of the determinant simply as being the volume of that parallelepiped that the cube turns into. A determinant of 0 would mean that all of space is squished onto something with 0 volume, meaning either a flat plane, a line, or, in the most extreme case, onto a single point. Those of you who watched Chapter 2 will recognize this as meaning that the columns of the matrix are linearly dependent. Can you see why?
Oh, yeah. Yes, we can clearly see it why. Because this vector here is the sum of the 2.
What about negative determinants? What should that mean for 3 dimensions? One way to describe orientation in 3D is with the right hand rule. Point the forefinger of your right hand in the direction of I hat, stick out your middle finger in the direction of J hat, and notice how when you point your thumb up, it's in the direction of K hat. If you can still do that after the transformation, orientation has not changed, and the determinant is positive. Otherwise, if after the transformation it only makes sense to do that with your left hand, orientation has been flipped, and the determinant is negative.
Yeah.
So if you haven't seen it before, you're probably wondering by now, how do you actually compute the determinant? For a 2 by 2 matrix with entries A, B, C, D, the formula is A times D minus B times C.
Yeah, that's what we
Here's
did
part of an
before.
intuition for where this formula comes from. Let's say that the terms B and C both happened to be 0. Then the term A tells you how much I hat is stretched in the x direction, and the term D tells you how much j hat is stretched in the y direction.
Oh,
So,
okay.
since those other terms are 0, it should make sense that A times D gives the area of the rectangle that our favorite unit square turns into, kind of like
Yes.
the 3002 example from earlier. Even if only one of B or C are 0, you'll have a parallelogram with a base A and a height D, so the area should still be A times D. Loosely speaking, if both B and C are non-zero, then that B times C term tells you how much this parallelogram is stretched or squished in the diagonal direction. For those of you hungry for a more precise description of this B times C term, here's a helpful diagram if you'd like to pause and ponder.
So we have. Wow.
Now, if you feel like computing determinants by hand is something that you need to know, the only way to get it down is to just practice it with a few. There's really not that much I can say or animate that's going to drill in the computation. This is all triply true for three-dimensional determinants. There is a formula, and if you feel like that's something you need to know, you should practice with a few matrices, or, go watch Sal Khan work through a few. Honestly, though, I don't think that those computations fall within the essence of linear algebra, but I definitely think that understanding what the determinant represents falls within that essence. Here's kind of a fun question to think about before the next video. If you multiply two matrices together, the determinant of the resulting matrix is the same as the product of the determinants of the original two matrices. If you tried to justify this with numbers, it would take a really long time. But see if you can explain why this makes sense in just one sentence.
Right. Also, I still have to understand how the determinant works. So we have a visual representation of the determinant, right? And if we and as we also wait, the determinant is only applies to square matrix, right? Determinant matrix conditions. It must be square, exactly. So let's go on YouTube and let's try to find the determinant here. So let's watch a video about it. So there is this, yeah, do we have,
Today I'm going to teach you about the matrix.
oh my god, are we serious? Andrew Tate is gonna explain me this? Oh god.
Today I'm going to teach you about the matrix, and not the one that tried to attack me.
Is that a matrix?
Correct.
This one has 2 rows and 2 columns, right, Andrew?
Yeah, that's correct. Now listen, if we multiply a matrix by a vector, this will transform the vector.
Wait, hold up. That's not a vector. A vector's like something times I plus something times j.
It's just another way of writing vectors, bruv. This one would be 1i plus 3j. So as an arrow, it'd look like this.
Oh, how'd you do the multiplication?
Just multiply each row of the matrix by the vector column.
Whoa, what do you mean by that? Well, hold on a second.
Yeah, how are you gonna times a row by a column?
You just times the first 2 numbers in the row and column, then times the second 2 numbers, and add everything together.
The first matrix row multiplied by the vector column gives us the number that goes here.
And then the second matrix row multiplied by the vector column gets us this bottom number.
So by multiplying the matrix by our original vector 1, 3, we've transformed it into this new vector minus 3, 1.
Oh, so this matrix turns vectors anti-clockwise?
A perfect 90-degree rotation.
Is there a way to know what transformation the matrix is going to do just by looking at it?
Yeah, so this red and green arrow are our basis vectors, right, with coordinates 1, 0, and 0, 1. Now watch me multiply the matrix by each one and transform them. So that's the first one done.
Don't stop cooking.
There's the second one done. So any vector we transform is just going to follow the basis vectors, right? Now look at the first column of the matrix. Notice how that's where the tip of the red basis vector ends up, and the second column tells us where the tip of the green basis vector ends up.
That's cool, but it didn't explain the determinant because it's not even written here. I'm dumb. Okay. Fuck you, YouTube, for recommending unrelated videos. I want to know how to calculate the determinant. So let's do this part here.
In this video, we're going to focus on finding the determinant of a 2x2 matrix and also of a 3x3 matrix.
Can we, is this, like, can we apply for every single process, like?
So let's start with the basics, the 2x2 matrix. Here, let's say this is A, C,
So,
positive 20.
yeah, we multiply these terms and then we subtract, and we already know that, right? But now let's focus on 3x3 matrices.
So let's go over the formula first. The first thing we want to do is get rid of the first row and the first column. And notice what you have left over. B2, C2, B3, C3. So you're going to use A1, and it's going to be reduced to a 2x2 matrix. So it's going to be A1, and then B2, C2, B3, C3. So when you cross out row 1 and column 1, you'll be left with B2, C2, B3, C3. Now let's move on to the next one. So it's going to be minus. So instead of using A1, we're going to use B1. B1 is in the first row and the second column. So what's left over is A2, A3, and C2, C3. That's going to be in the next 2x2 matrix. So it's going to be negative B1, and then A2, A3, C2, C3. And then plus, the next one is going to be C1. C1 is in row 1, column 3. So what we have left over is A2, B2, A3, B3. So it's going to be C1,
Okay, that's pretty easy.
A2, A3, B2, B3. And then you know how to evaluate a 2x2 matrix, because we covered that already. So now let's work on an example. So let's say we have 2, 4, negative 3, 5, 7, 6, negative 8, 1, and 9. So feel free to pause the video and work on this example.
Okay, let's do that. Let's find the determinant of this matrix. So let's go here. So we have this part, right? We have 2, 4, minus 3, then we have 5, god fucking damn it, 5, 7, 6, minus 8, 1, 9. So the first thing we should multiply 2. Also, wait. When we should we always subtract this part? Like the second part is subtracted, right? Yeah. So we have -8 right here. Now we have to compute this. 7, 6, 1, 9. Right? Then we have, let me move the chat. Then we have -4, and it is computed like this. So we have 5, 6, -8, and 9. And then we have plus -3. I mean -3. And then we have 5, 7, -8, and 1. So that's basically what we did, right? It is like this. So now we have to make this multiplication, right? So if we do it by a scalar, we have to, should we sum the values? Wait. So this is a 1 by 1. And then we have a 2 by 2. So the result should be 1 by 2. Wait, what? No. It's another type of multiplication. This is a dot product. But a scalar product is different. Okay. So if we multiply this with a scalar value, it should be like this, right? Yeah. So this doesn't apply for matrices. Not sure, but let's try that. So right now, we simply have to do this. 14, then we have 12, then we have 1, then we have 9, right? Then we have 20, we have 20, right? Oh my god. Then we have 6 times 4, it's 24. Then we have 32 minus negative 32, and then we have 18, probably 36, right? Then we have negative 15, then we have 21, then we have negative the fuck is this 24, right? Yeah, and then 3. Then what we need to do, we just need to compute these operations. So we have 14 minus 20, it's minus 6, plus 15, and it's 9, right? Yeah, it should be like that, right? Actually, this is a negative number. So we have minus 6 and it should be minus 21. Negative 21, right? So we have this and this. And the sum is negative 45 plus 12. So it should be like this, right? Wait, let me just... Yeah, it's like this. I just want to make sure, right? Now we have this plus 32, so we have um, we have 1 plus 32 plus 24. So these two added together is 56 plus 1. And the last one is 9 plus 3, 12, and it should be 48. Right? So after we did this, what else should we do? Oh, that's the wrong video.
Because we covered that already. So feel free to pause the video and work on this example. So we're going to use 2 first. So it's going to be, we're going to put the 2 in front. And once we use the 2, we need to get rid of row 1 and column 1. So we're going to use 7, 6, 1, 9. So that's going to be inside the 2 by 2 matrix. And then minus. Now we're going to use the 4. And we're going to get rid of row 1, column 2. So we're going to have 5, negative 8, and 6, 9. So it's a minus 4, and then 5, negative 8, 6, 9. Now the next number that we have is negative 3. So we're going to get rid of row 1 and column 3. So we have a negative 3 on the front, and then we're going to write what we see here. 5, 7, negative 8, 1. So that's how you can simplify the 3 by 3 matrix into 3 2 by 2 matrices, or matrices. Now let's evaluate this 2 by 2 matrix. So it's 2, and then it's going to be 7 times 9 minus 1 times 6. So multiply these two first, 7 and 9, and then minus 1 times 6.
Wait. What?
The next one's going to be 5 times 9 minus negative 8 times 6. So first we have a negative 4, and then 5 times 9 minus 6 times negative 8. And then we're going to have negative 3 times 5 times 1, which is 5, minus negative 8 times 7, which is negative 56. So 7 times 9 is 63. 1 times 6 is 6. 5 times 9 is 45. Negative 6 times negative 8, that's positive 48. And then we have 5 minus negative 56, which is like 5 plus 56, so that's 61. 63 minus 6, that's 57. 45 plus 48, that's going to be 93. Negative 3 times 61 is negative 183. 2 times 57, that's 114. And 4 times 93, that's 372, minus 183. So if we go ahead and combine these last three numbers, this is going to give us negative 441. So that's going to be the determinant of the 3x3 matrix.
Okay, that's... So we have to compute this operation. I don't know if I'm doing this right, but what if we compute this? I don't know. What if we compute these operations, right? I don't know what's gonna happen. It's definitely something wrong. I don't know. I'm gonna try, but I doubt this will return the right result. So what if we have minus 21 can you fucking... So we have minus 21 times 48. And we get this value. No, it doesn't. This isn't right. So we simply have to evaluate these values, right? Honestly, I didn't know that. Why is it different though?
So the first number is going to be 5. And if we get rid of the first row in the first column, we're going to get -3, 6, 7, -9. Next, we're going to use the 7. So if we take away the first row in the second column, it's going to be 4, 1, and 6, -9. And then the last one, -8. So if we take away row 1, column 3, we're left with 4, -3, 1, 7. Now let's go ahead and evaluate the 2x2 matrices. So first we have -3 times -9, which is +27, and then minus 7 times 6, which is 42. And then it's going to be -7 times 4 times -9, that's -36, minus 6 times 1, which is 6. And then this is going to be -8. 4 times 7 is 28. And then 1 times minus -3. 27 minus 42, that's -15. -36 minus 6 is -42. And 28 minus -3, that's 28 plus 3, that's 31. 5 times -15,
I actually muted myself. When did this happen? Oh my fucking, I swear to fucking god, I'm gonna do something. Let me just reopen this. This shit just fucking crashed. Oh my fucking god. So, here we are. Also, fuck you OBS for muting this shit. So let's keep going with the fucking. Also, when did this happen? Like, let me just check the. Uh, also, when did. So I was muted the whole time. I was fucking muted the whole fucking time. This values, right? Something wrong. I don't know. I'm gonna try, but I doubt this will return the minus strength. Why is it different though? I press something and I get muted. Stupid fucking shit. Get the fuck out of here. Oh my fucking god. Fucking stupid fucking OBS. Fucking suck.
So if we take away row 1, column 3, we're left with 4, negative 3, 1, 7.
Let's check this. What do we have? Yeah. Everything
Now
is.
let's go ahead and evaluate the 2x2 matrices. So first we have negative 3 times negative 9, which is positive 27, and then minus 7 times 6, which is 42. And then it's going to be negative 7 times 4 times negative 9, that's negative 36, minus 6 times 1, which is 6. And then this is going to be minus 8. 4 times 7 is 28. And then 1 times negative 3 is going to be minus negative 3. 27 minus 42, that's negative 15. Negative 36 minus 6 is negative 42. And 28.
Wait, what the fuck? How is that negative 15? Right. This fucking shit confuses me. You know what? Fuck off. Yeah, it is minus 15. For some reason, I thought this was minus 25. Holy fucking shit. I have to do this again. Fuck this shit. So we have 25 and then 50, so it should be 75. Now let me just... Where the fuck is the calculator? Did I fucking close the calculator? Or did it crash? I don't fucking know. Let me open this shit. So we have this. So now let's try to... So that's the difference. So we have to... This should be... You know... It should be 29, right? Not sure. Let's try that out.
Minus -3, that's 28 plus 3, that's 31. 5 times -15 is -75. -7 times -42, that's positive 294. And 8 times 31, that's -248. So if we combine these three numbers, this is going to give us -29 as our final answer. So
Yeah.
that's the determinant of the 3x3 matrix. By the way, if you want to get more videos on algebra, trigonometry, pre-calculus,
I don't fucking know why. Also, I'm not subscribed to this channel. I thought I subscribed. What?
today,
They fucking removed my subscription. What the fuck? You stupid fucking YouTube. Subscribe to this fucking channel. So that's basically it. Like, Jesus, for some reason, like, if we perform 20 minus 30, the result is minus 10 is negative 10. Like, it's actually negative 20. Wait, how does that work? Hold on. This is I know this is confusing. So this is like this. Right? This is pretty much like we subtracted the first value, right? We have 27 minus 42. Like, okay, I know why I got confused. I know why. Because minus 15 is greater than minus 20. So on the positive numbers, even if 7 minus 2 is actually greater than 0, that doesn't mean that it will remain 20 because this is a negative number. Yeah, that was a fucking dumb error. I don't know. For me, this shit is confusing. I don't know why. Don't fucking... What the fuck is wrong with you? Holy shit. So let's keep going. And let me check if I still... Okay. So that's pretty much how it works. We found the determinant of a matrix. But what if we want to find a determinant of a 4 by 4 matrix? Before I showed you like how I think it is the best way. Not the best way, but one of the you know of the ways to do it. Let's try to find it out.
In this video, we're going to talk about how to find the determinant of a 4 by 4 matrix. Now, the first thing you want to do is identify the row or the column with the greatest number of zeros. In this example problem, we can't find any rows or columns with 2 or more zeros. So I'm going to start with the first row, just to keep things simple.
Wait, what?
With 2 or more zeros, a 4 by 4 matrix. Now, the first thing you want to do is identify the row or the column with the greatest number of zeros. In this example problem, we can't find any rows or columns with 2 or more zeros. So I'm going to start with the first row, just to keep things simple. Now, the 4 numbers that you see here in the first row, these are going to be used as the coefficients for when we form the 3 by 3 matrix. So let's start with the first one. The first coefficient is 1.
Wait, the fuck is. Hold on.
-2, 3.
Wait, that's the thing that I explained, right? Yeah, it's pretty much the same thing, but we should. It's like a nested calculation, right? So this also applies for the 5 by 5 matrix, and so on. Like we actually get the idea, right? So we kinda know how to find the determinant, right? So can we do this calculation right here? So now we have to find the determinant, right? Of a matrix, right? So this is the matrix. What the fuck? Okay. Oh my god. So to do that, let's go here and let's implement the function to calculate the determinant of a matrix, right? We have it right here. Wait, what the fuck am I doing? Oh my fucking god, don't. Why don't do I do. Why do. Why do I do things without thinking sometimes? So this will return a scalar value, right? So to find the determinant, the first thing we should check if the matrix dot rows, we should check if this is a square matrix by doing this. If it's not, what should we return? Like, we return 0. But actually, I don't wish it's not 0, but it's an invalid value. But in this case, I will just return 0. So now what we have right now, we have like a matrix, right? So we should think about what we can do to reduce this, right? So this is actually a recursive function, right? Because we can clearly see it. You can clearly see it right here.
We're going to talk about.
If we go here, like this evaluates into this, right? Oh, luckily this is 0, okay. So we have 74, and this is evaluates this as 74. We technically calculated the determinant of the determinant of another determinant, right? And we combine the results. So the same thing is doing it right here, right? And that's pretty much it. So the more we increase the matrix, the more nested determinant are, right? This is pretty much how it works. So to do that, we should probably check if the matrix, the rows, is equal to 2, right? And we don't need to check if the columns are also equal because we already did this check, so they must be equal. So if they are, we will return, right? We should return this expression. So matrix dot we should return matval, right? 1 1 times hold on. We should return this, right? Times this, right? Minus this, and this is actually this, and then this. So this is pretty much how it works. Then if it's not the case, we have to calculate the sum, right? We definitely need to create the matrix. Wait, we have a set of matrix, so we probably have something like this, and we should get a fixed size of an array. Like we don't have a fixed size of an array, so we have to allocate this dynamically. So we simply do malloc and then we will return probably matrix dot rows minus 1, and this is multiplied by sides of this. Yeah, that makes sense, because what we on the first process, oh my fucking god, in the first process we are technically, we have this part, right? Then we have the first number, then we have the second number, the third term, and the fourth, right? So we should get the first matrix, then we have probably the second matrix, like this. Oh wait, like this. Then we have the third matrix, and it will probably like this. And then we have the fourth matrix in this example, right? Let's put 3 other terms right here just to. So every time there is this division, we should put a negative number, right? No. It's actually alternate, like it alternates, right? I'm not sure, but we definitely need wait, we need 4 of them, so definitely we need this amount of matrices, right? But so we perform a for loop like this. I don't know if I should do it like that. Then we have this, right? Probably is this operation allowed? I think I should wrap this inside this expression. And then we have to, no, I mean we have this part right here. Then we have create matrix, right? And the size is matrix the rows minus 1, and then we have matrix dot columns minus 1. So we should create new matrices, right? And then we should assign the right value. Probably like that. This won't be that easy. So with the determinant, we mean the area that is changed, the factor of change of the area, right? So to do that, we definitely need to sum the results, okay? So let's create the results and let's assign it to 0. So then we have to iterate, we have to sum the result, and probably I don't know if this should be okay, but I'm gonna multiply the determinant, right, of the of course I will perform some calculation here. So we have to find the determinant of this matrix, right? Actually, should we allocate this dynamically, or we can just, you know, I think we can just create a new matrix like that, right? Yeah, that would make sense. And this is multiplied, but for what I can see, like that. Not sure though, but for what I see here, it's, you know, you start with a positive term, then you have a negative term, and you have a positive term, and then again a negative term. If the also we have to get this value, so we have this value right here. Oh, of course we will return the results like this, which is the, I don't know, coefficient. I will call it C. And actually it's, the value is, we can just get the matrix dot data. Wait, what the fuck? Oh, matrix dot data at I. Would be more correct if we wrote columns, but it's guaranteed that these two are equal, so don't really care. But let's use columns, right? So this is the Yeah, this is pretty much how it works. Now, the only thing that we need to do, we have to assign, to set this little matrix, right? And it's actually not that easy to handle because it's not that immediate, because we have to check if we have like other matrices here. Like these two split matrices are quite confusing. Oh, so what if we get a 5 by 5 matrix? Okay, this will be very complicated, right? Oh, we have the triangular matrices. Okay, that will be, so this is a simple multiplication. So you have 3 times minus 2. So the determinant is, we can already, for triangular matrices, you can already find the determinant, okay? Oh, we have to do this operation. I'm really not sure how is this gonna work. I will find it out. But at least we know how to do it for 3 by 3 and 4 by 4 matrices, right? Mainly 3 by 3. So yeah. Still trying to get this concept. There are many ways to find it for, you know, to find the fucking determinant, but what the fuck is this? I'm done. Oh my god.
Okay, so this is going to use a combination of techniques, but the main thing is that we're going to still use the cofactor expansion. Okay, so like I said before, okay, you want to use the row or column with the most zeros. Okay, so we can see just at glance here, we can use the second row here. Okay, so we're going to focus.
So we still have to find the column with the most zeros, the rows and the column with the most zeros. So we have this, and then we have this, right?
Focus on that one. Okay, so I'm just going to go ahead and just mark this one.
What the fuck
Okay.
is this?
So, and okay, so that's using this. Okay, so starting with this value, and let's recall the sign conventions. So we have plus, minus, plus, minus, plus, plus, minus, plus, minus. Okay, so this is for 5 by 5. Okay. All right. Okay, so we start with 2, okay? So that's going to have, for that particular cofactor, we need the value, we're going to use, it's going to be minus 2, okay? So minus 2 times the determinant of the
So this is where we
submatrix. So it's going to be 4, 0, 3, minus
and
5.
then this part, and then this part.
7,
right?
3, 4, negative 8, 5, 0, 2, negative 3, 0, 0, negative 1, and 2. Okay. So again, we're using the second row because those are the ones with the most 0. I could have
Right.
also used the second column. Regardless, it's going to give you the same result. Okay. All right. So now we need to find the determinant of this one. Okay.
So we also have to split this too. Okay.
And that's the only one because 2 is the only non-zero value in that particular row. So once we find the determinant of this, then we're done. Okay. So going over here. Okay. So I'm gonna go back to this. Okay, so let's focus on this determinant.
Oh, that's why we choose the row or the column with most 0, because the other values the other matrices cancel out automatically, right?
Let me use green here. Okay, so I have 4.
On the algorithm we were gonna write it on C. I don't think this is really convenient to. I don't think that it is a good idea to check if there are zeros, because this could be a problem. Checking if there are zeros it's expensive, actually.
0. Oops.
So yeah, in this case, after we find the determinant of this matrix, we just have to multiply it by -2, and then we have, of course, we have to find the determinant of this 3 by 3 matrix, and then of this part right here. This is actually really easy to do it. So yeah.
3 minus 5. 7, 3, 4, negative 8, 5, 0, 2 minus 3, 0, 0 minus 1, and 2. Okay. So again, we need to find the determinant of this one. And again, so notice that the second column here has only one non-zero value.
So we are gonna take this, right? And then we construct the matrix.
I want to use that to help us find the determinant. Okay. All right. So focusing on this one. Okay. Okay. So using the sign convention. Remember, so this is for the 4 by 4. So this is plus, minus, plus. Okay. So this is going to be plus.
How does that work? You have plus, minus, then plus, right? Wait.
3. Okay. Times the determinant.
So this is plus, then we have minus, and then we have plus 3. Okay.
Determinant of the submatrix. 4, 3, negative 5. 5, 2, minus 3, 0, negative 1, 2.
So actually what we did here is actually correct. That's crazy.
Okay. So for this, matrix, we can use that diagonal line approach. Okay. So let's do that down here. So once we get that, okay, we plug it, we multiply it by 3, and then we plug it back into here and multiply it by 2, by -2, and then we'll get then that will give us the determinant of A.
Yeah, exactly.
Right, so we have 4, 3, negative 5, 5, 2, minus 3, 0, minus 1, 2. Okay, so I'm using that diagonal line approach. So I'm going to take the first column, put it here, take the second column, okay, and place it here. Okay, all right, and then multiply. Okay, so let's draw our diagonals.
I'm not aware of this method. Wait, let me.
First, okay, so I'm using that diagonal line approach. So I'm going to take the first column, put it here, take the second column, okay, and place it here. Okay.
Okay.
All right, and and then multiply. Okay, so let's draw diagonals. All right, so we're gonna get, remember that we're gonna subtract these. So 0, we get 4 times minus 3 times negative 1. That's gonna give you positive 12. Here we get 2 times 5, 10 times 3. That would give us 30. Okay, and then we're going to add to these. So 4 times 2 times 2, that's going to give 16. We have a 0 here, so that's going to give 0. And then negative 5 times negative 1, that will give you positive 25. Okay, adding those up, okay, you get minus 1 here. Okay.
So is that the determinant of this matrix?
So that is, okay, so that's going to go back into here, all right? And then we're going to multiply by 3 and then multiply by minus 2.
Okay. So it's 6.
So therefore,
oh, wait. Yeah, it's 6, right?
the determinant of A is minus 2 times 3 times negative 1. So we end up getting the determinant of 6. Okay.
That was really easy. Like, I didn't know it was that easy. So the only thing we need to do is to construct the matrices that are contained in the outer matrix, right? Then we can choose we can choose a row or a column to perform these operations, right? Because if we find like 4 zeros here, it's gonna get us like, it is gonna be like efficient for us, right?
So that's how it works for finding a matrix of something larger than a 3 by 3. It's a recursive process.
Yeah, that's what I said before. It's a recursive process. That's why we call this function right here.
Okay, so you just keep applying the formula, okay, until you get something down to something smaller, and then you go back and plug in those values at the end. Okay.
That's cool. So we basically know everything about the determinant, right? So let's try to write the script that does this for us, right? The other thing that we have to do is to construct the inner matrix. So what we are going to do right now. So let's suppose we are on this case, right? I will do that blue. So we have to start from, we probably need a for loop, right? Yeah, we definitely need a for loop. Actually, we need a nested for loop. So Let's see if we can do this. Uh, you know what? Let me replace this with H. I think that in this case it would be much better to call it H, right? So now we have size T, I, 0. Then we have, actually this should be 1. Then we have this. Then we have the matrix columns, right? And then we have I++. Actually this should be -1, right? And then we have size T, J, 1, and this time J should be, actually this should be 2, right? Then we have matrix dot rows. I know this sounds confusing because usually we use I to indicate the column, the rows, not the columns. Right? So to not get confused, let's actually put this like this, right? And we have rows and we have the columns right here. Oh god. I think this will be better, right? And why the fuck did I put this? Don't even remember, honestly. It should be, probably should be right there. Yeah, this probably makes sense. Yeah, probably, yeah. So now we have to fill the inner matrix, right? So we have this. Actually, we have this macro. Then we have the inner matrix. I call it sub. And we have I and J. Actually, the value should be let me just do this. I think this will be much better. Yeah, it will be less confusing. So now what we need to do is ensure assign this to mat val this action matrix Then we have I plus 1, right? And here we have J, and actually J should be like less than C, right? Not sure if that works. But it should be like this, right? I don't know. So let's give it a try. So what if we want to find the determinant of this matrix, right? So we have this part, right? Let's remove this. Okay, this is related to determinants, right? And let's leave it right here. Right. Let's leave it there. Okay. So let's try to create a matrix, right? Let's create a matrix T E. Also, I forgot to delete the matrix. We should actually delete the matrix once we used it. We will delete this sub, right? The hell? Oh, right. We should probably declare this outside because allocating memory could be a problem. Like dynamic allocation are pretty slow. Wait, what the fuck? Wait, what? Why is this? Oh right, I have to pass the address. Okay. So let's create a new matrix. So let's create a matrix, and it will be a 3 by 3 matrix, right? And now let's set the matrix. Let's add E like this, right? Now let's assign the values. So we have 5, 7, minus 8. Then we have 4, negative 3. And then we have 6 right here. Then we have 1, 7, negative 9. So what happened if I wanna find the determinant of this matrix? I don't know what will happen. And this actually a scalar. This is actually a number, so we can just use printf percent f, and then we print the determinant of E, right? So we have the determinant of E, and then we will find the result. right? Not sure if that works, but let's try it. And the determinant is 15. No, it's not 15. Jesus! Let me try to print the matrix. So let me just printf also, this that we have printf, print matrix, and we have the action matrix, right? Oh god fucking damn it. What happened if we do this? Let's try it. No. What the fuck? Bro. Why do we get... Why do we get another 3x3 matrix? Wait, what? What the hell? Oh, this should be right there. I should put this right here. So let's try to... So let's see, we have... Oh, I know what's going on. So I actually selected the wrong values. Dang it. So I did the good thing here, but actually I selected the wrong values, and for some reason this is a 3x2. This is a 3x2 matrix. I know where the mistake is. I have to select the right values. Let me just print percent u. Wait, f. We will print c. Right. Let's try it. What the fuck? What the hell? I don't think this is supposed to happen. So let's print that here. And let's try again. Okay. So we have 5, right? But the selected values are actually not correct because it selected this. This two got selected, right? No, this got selected. Then we have for 1. Then we have this. For the second value, this is actually correct, but for the third one, it is not, because it just selects this, which is wrong. Let's see. Maybe we should probably. Oh god, fucking damn it. So we have this part, right? Then we have to take this part and this part. And okay. So what if um so we have I plus 1, right? Now this makes sense. And the thing is that this part should be fixed, right? So let's focus on this part. So if J is okay, so J should actually be actually, what the fuck am I doing? I should multiply this value somewhere. So we should probably multiply this by C, right? And this should be H. This value should be H. I don't think this is gonna work. So we still have, oh wait, we actually have the right value selected. No, actually not. Probably this should be I. Let's try again. It's fucking not. this one should be H, actually. I don't fucking know, like, we have this value, right? And for some reason, they're the same value. They have the same value. I really don't understand why does this shit happens. Fucking sucks, dude. Don't know what if we put this, but I doubt this is gonna work. I actually have some different results. So we have, this is -3, 7, 6, -9. Then we have 7, 4, 1, 6, -1. Oh my god, it works. It works. The determinant is 9. Okay. Okay. That's interesting. That's interesting. It almost works. Like, the result is the actual result is -29, but we got 29. So we are getting close. Right? Actually, this is when this is wait. Let me just do this and let me try again. Okay. It works for this matrix, but now we should test for larger matrices, right? Let's test with a 5 by 5.
So now.
Okay, let me just. So we have this. The result should be 6, right? Okay. Am I still streaming? Okay. Let me just check if I actually am. So let me just check my YouTube channel. Okay, I'm still streaming. That's good. So now what we need to do, let's try to put that here, right? Let me just check if I'm not muted. Okay. So let's create, let's do the same thing we did here, right? We create F, and this is a 5 by 5, right? And then we have this. Now we have to copy this matrix. So let me just rewrite this from scratch. So we have 4, then we have 0, -7, 3, -5. Now we have 0, 0, 0. Wait, 2. Then 0, 0. Then we have 7, 3, -6, 4, -8. Right? Then we have 5, 0, 5, 2, negative 3. Then we have 0, 0, 9, negative 1, and then 2. I don't know. And fuck. Fuck, this is not good. The fuck is it doing? Wait, what the hell? Actually, this is... Oh, wait. Wait. I just forgot to replace this. And let's try again. Let's see what we get. Holy shit, oh my fucking god, it works. It actually works. No fucking way. No fucking way. Wait. Is that true? Is that true? Is it 6? Yeah, it's 6. It works. Wow. So this is the algorithm to calculate the determinant, right? Let's remove this part, and that's it. That's the algorithm we need to calculate the determinant. It's a recursive function, and it's just take this data, get a matrix from another data, and then pass it and then calculate the determinant of the inner data. So don't know how to explain this properly, but we did it. That's basically how it works, right? Also, I need to get rid of this print. Here we are. So we managed to calculate the determinant of this matrix. That's actually really cool. So yeah. Now we know what that is. We know that. We know what a determinant is, and also we know physically what it is. Like, it's the factor of change of the area of a square unit, right? So if we go back here, that's basically the determinant. Like, if we change this, it is still the determinant. Like, the determinant is the same, right? But on this matrix, the determinant is actually 2, right? Because we transformed this. Actually, it's negative 2. Let's see if that's true. So let's create a new matrix, right? So we have, hold on, let me just sort this properly so don't get confused. So let's create a 2 by 2 matrix, right? And then we assign 0, 1. Then we have, oh wait, this is 2. And then we have 1, 1. So the determinant for this matrix should be -2, right? This is actually pretty simple to calculate. And there should be any issue because this is a 2 by 2 matrix. So, but let's use our software. We find it as that is 0. Wait, what the hell? It should be negative actually. Why is it 0? If we multiply this and then we subtract this, actually it's -2. That's an issue, honestly. Oh wait, I'm fucking dumb. So let's try again. Yes, it is. It is -2, right? Yeah. Yeah, we also managed to create the determinant function in C. That's good, isn't it? So now we know what a determinant is. So yeah. Let's move on. Like, we know everything about it now, right? Then we already know the multiplication by scalar, right? Then we have the compact representations of system of linear equations, right? And as we read before, we have this format, right? This is the format how we represent the linear equations. We have the unknown values on this vector. Then we have the matrix containing the coefficients, and then we have the actual result, right? Pretty simple. So yeah, I think I'm gonna take another short break because yeah, I managed to create this function, and that's cool. Like wow. Yeah, I'll come back in a few minutes. So I'll be right back. Okay, we are back again. So now we have 1 hour left, right? Because we reach 6 hours, right? Right. So I'm it's I'm just very happy that I I know what a determinant is and how to calculate this using, and we did the algorithm to do that in C, and this works for, apparently this works for every type of matrix. Of course, it should be a square matrix, or else the result will be 0. And that's actually good. So now let's move on. And let's read the. Okay, we already read this, and let's read this part. Let's read the solving systems of linear equations. So in 2.3, we introduced the general form of an equation system, and it is something like this, right? We have, we probably have a matrix of coefficients, and that is multiplied by a vector of unknown values, and this gives us a vector of results, right? And they turned this into a matrix transformation, right? Into a vector transformation, where this is a real number and b is also a real number, and a and b are known constants, right? And x are knowns. So I is 1 is from 1 to m, and j is 1 to n. Thus far, we saw that matrices can be used as a compact way to formulating systems of linear equations, so that we can write ax equals b, as we said before. Moreover, we define basic matrix operations, such as addition and multiplication of matrices. And we wrote the algorithms in C to do that, right? So we know how to do this. In the following, we will focus on solving systems of linear equations and provide an algorithm for finding the inverse of a matrix. So that's cool. So now we will use this as stated here, the matrices to solve, right? Solving linear equations and provide an algorithm for finding the inverse of a matrix. This is interesting. The algorithm for finding the inverse of a matrix, right? So we have the particular and general solution. Before discussing how to generally solve systems of linear equations, let us have a look at an example. Consider the system of equations. So we have the system of equations. As we can see before, it's a valid multiplications that gives us a 2 by 1, right? So consider the system of equations. So we have this. These are the coefficients. So we have like x1 plus 8x3 minus 4x4, right? And then we have this is we can wait. Let me just rewrite this as a normal equation, right? So let's take this space, right? Let's go here. Let's just use this space. So let's rewrite this as x1 plus 8x2, or we can just leave some space just to make it. What the hell is going on? Why is it? I don't know. Sometimes it just, I don't know. So then we have 8x 3 minus 4x 4, and this is equals to 42, right? Then we have x2, right, plus 2x3 plus 12x4, right? And this gives us 8. The system has 2 equations and 4 are nodes. Therefore, in general, we would expect infinitely many solutions. Yeah. This system of equations is in a particularly easy form, where the first 2 columns consist of a 1 and 0. Yeah, that's true. Remember that we want to find scalars. So we want to find each scalar in this vector, right? Such that the sum of these scalars multiplied by c is b, where we define c to be the ith column of the matrix and b the right hand side. Okay, this is b, right? I don't wait. What is c? Is the ith column of the matrix, so c should be like this, right? Should be this, yeah. And then we get this. A solution to the problem in 2.38 can be found immediately by taking 42 times the first column and 8 times the second column, so that wait, what does that mean actually? So yeah, we find this solution, right? But why only the first 2 columns? So we have x, right? Is equal to b. Honestly, I don't know. Therefore, the solution is this vector. This solution is called a particular solution or special solution. However, this is not the only solution of this system of linear equations. To capture all the other solutions, we need to be creative in generating 0 in a non-trivial way using the columns of the matrix. Adding 0 to our special solution does not change the special solution. To do so, we express the third column using the first 2 columns, which are of this very simple form. Yeah, probably. Okay. Okay, I still trying to understand this part. So I'm still trying to understand this part right here. So what do we have right now? Um, let me check something here. Okay, so we have two types of solutions, right? We have the general solution. Try to understand like what's the actual point of this. Like, so we have the summation of this, right? So this is a vector. So this is a vector. So we have 1, 0 multiplied by x1, and this is equals to 42, right? Yes. Yes, this is what it's written right here. Exactly. But I don't understand why it is taking the first two columns. I don't understand why are we just taking the first two columns and not the other ones. What the hell? Uh, The fuck is going on actually? I really don't understand this part. I don't know why it does this. Like, let me reread this part. So C is the ith column of the matrix. B is the right hand side of this. This is B. So these are the vector C, right? These are the vectors C, which is the column. We define C to be the column, and I already know that, but I don't understand why a solution to the problem can be found immediately by taking 42 times the first column and 8 times the second column. Like, why are the other values gone? Like, I really don't understand. Why do we eject these 4 elements, the other 2 columns? I don't understand. Probably because they are 0. No. I don't. Wait, no. So yeah, okay. The thing I understand is that if we take this solution right here, the other terms must be equal to 0, right? So x3, like 8x3 plus, minus 4x4 should be 0. And the same thing applies to this, right? And this solution will automatically become true. Why is this solution is called particular solution or special solution? However, this is not the only solution of this system of linear equation. So I'll capture all the other solutions. We need to be creative in generating 0 in a non-trivial way using the columns of the matrix. Yeah, we should make this turn 0, right? Exactly what we did here. Like, we have the sum of this part, right? And this should be 0 if we want to make that true. Following the same line of reasoning, we express the fourth column to the matrix in using the first 2 columns and generate another set of non-trivial versions of 0 as the fuck, honestly. So, for what I can understand is that there are. I only understood that there are particular solution or special solution, but But honestly, I cannot get it. Like, what is this? Why do we have these values? Where does -1 come from? Oh wait. So all of this is I'm just trying to understand. Like, I also have vector subspaces right here. And we have complex numbers. And we have the definition of linear independence. Damn, I wanna reach this part. Okay, I also saw the Gaussian elimination. So let's try to find something on YouTube about the particular and general solution, right? So we have something like this, right? Also, what do we have next? Let me just check. Oh, that's interesting. Uh, so I'm still streaming though. Yeah. Uh, this is. I don't think this is English. This is differential equations. So this is related to differential equations, right? So there are four types of solutions for what I can understand. Let's try to watch the video.
Let's say we know about the derivative of a function, and let's say f prime of x is equal to 2 over x cubed, and someone comes up to you and asks what is f of x, what can f of x be, and the immediate answer that you should give your friend or your wife or your husband is that f of x is the integral of 2 over x cubed dx. Remember, integral of 2 over x cubed dx is a function that if you, or a family of function, that if you take derivative of, you get 2 over x cubed, and that's the function that you wish to find. And how do you find integral of 2 over x cubed dx? You start by getting constant outside the integral, so you have 2 times integral of 1 over x cubed, rewritten as x to the negative 3 dx. And we know integral of x to the nth, we know integral of x to the something dx is same thing as x to the n plus 1 over n plus 1 plus c. So let's apply that. It's going to be x to the negative 3 plus 1 divided by the same thing, and you're going to put plus c. So this is going to be 2 times x to the negative second power over negative 2 plus c, also known as 2's cancel out and you got negative sign, and you put this at the bottom. You have negative 1 over x squared plus c. So we know if f prime of x is 2 over x cubed, our f of x is, what was it, negative 1 over x squared plus c. And we call this a general solution. And the reason it is general, it is not one specific or one particular solution. F of x can be negative 1 over x squared plus 5. F of x can be negative 1 over x squared minus 0.01. F of x can be negative 1 over x squared plus 10,000. We do not have a particular solution to pick from. But let's say in addition to f prime of x equals to 2 over x cubed, they also tell you f at 1 is equal to 3, and this is called the initial condition. And the reason f of 1 is equal to 3 is helping us pick a specific solution is when you look at this graph below. This is from desmos.com. Let me give credit. I have bunch of f of x is equal to negative 1 over x squared plus c graphed out. The orange one is negative 1 over x squared plus 2. The magenta one is negative 1 over x squared plus 3. The red one is negative 1 over x squared plus 4. The blue one is negative 1 over x squared plus 5. And the green one is negative 1 over x squared plus 6. And as you can see, and this is the point 1, 3. Only one of the graph, in particular, negative 1 over x squared plus 4, is going through the point that they gave you. So in this case, if we know f prime of x is 2 over x cubed, and also we know that f of 1 is 3, our f of x is not a family of functions, but one particular function, which is negative 1 over x squared plus 4. And this is called a particular solution, because we only have one solution we are talking about. Let's say we do not have this graphed out, and we don't know which graph is which one. Then how would you figure out the constant is plus 4? How can you figure this out? And that's not hard to do. It's by plugging in f of 1 is 3. In this case, we have f of x is negative 1 over x squared plus c. That's the general solution. And you can plug in x equals to 1, and you expect to get y of 3. So we want 3 to be equal to negative 1 over 1 squared plus c. I'm just plugging 1 into the function, and we want to get 3 out of it. So we have 3 is equal to negative 1 plus c, or c is equal to 4. So you know the particular solution is going to be negative 1 over x squared plus, instead of plus c, plus 4.
That's that 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 was a little bit, this video that video was a little bit weird, but I kinda get the points. Yeah, it's actually pretty simple. What the fuck? So let's reread this. A solution to the problem in this equation, in this expression, can be found immediately by taking 42 times the first column and 8 times the second column, so that b 42 8 is equal to 42 times 1 and 0. Okay. Yeah. Therefore a solution is, yeah, I agree. That's the solution, right? This solution is called particular solution or special solution. Okay, I get this part. However, this is not the only solution of this system of linear equation. To capture all the other solutions, we need to be creative in generating zero in a non-trivial way using the columns of the matrix. Adding zero to our special solution. Wait. Adding zero to our special solution does not change the special solution. To do so, we express the third column using the first two columns, which are of this very simple form. So if we look at this, we have the third column and it is expressed like this. So we have this part right here, right? So this part is just explaining the difference between general and particular solution and the way to find the general solution, right? So let's move on. Elementary transformations. Key to solving a system of linear equations are elementary transformations that keep the solution set the same, but that transform the equation system into a simpler form. Okay. So we have, wait. Oh, to simplify form. Exchange of two equations, rows in the matrix represents the system of equations. Multiplication of an equation row with a constant lambda that is different than 0, right? Adding addition of two equations rows. So what do we have? Okay. Oh, that's the Gaussian reduction. That's okay. This is where the Gaussian reduction the Gaussian elimination comes from. I know this. I know this. Wait, does it mention it? It mention it, right? Yeah. This is the Gaussian elimination. I think. I'm not sure though. I might be confused with something else. For A, which is R, and I think this is this part here, right? We seek all solution of the following system of equations. We start by converting the system of an equation into a complete matrix notation, right? Like this, right? We no longer mention the variables x explicitly and build the augmented matrix in the form A and B, where we use the vertical line to separate the left-hand side from the right-hand side. We use this to indicate a transformation of the augmented matrix using the elementary transformation. What symbol is this? Rightwards squiggle arrow. That's interesting. Swapping rows 1 and 3 leads to okay. I don't know what that means. What does that mean? Why do we have this free? The fuck is R? So we will end up with this notation, right? I don't know, I'm not sure. I will probably think about solving systems of linear equations later, right? Because the inverse of a matrix actually comes after all of this. I have some shit mixed up. Calculating an inverse of a matrix. Right? This is page 40 or 34. So yeah, we will look into this the next time. And now let's watch this video about inverse matrices. So let him introduce us to this part.
As you can probably tell by now, the bulk of this series is on understanding matrix and vector operations through that more visual lens of linear transformations. This video is no exception, describing the concepts of inverse matrices, column space, rank, and null space through that lens. A forewarning though, I'm not going to talk about the methods for actually computing these things, and some would argue that that's pretty important. There are a lot of very good resources for learning those methods outside. A forewarning though, I'm not going to talk about the methods for actually computing these things, and some would argue that that's pretty important. There are a lot of very good resources for learning those methods outside this series. Keywords Gaussian elimination and row echelon form.
Yeah.
I think most of the value that I actually have to add here is on the intuition half. Plus, in practice, we usually get software to compute this stuff for us anyway. First, a few words on the usefulness of linear algebra. By now you already have a hint for how it's used in describing the manipulation of space, which is useful for things like computer graphics and robotics. But one of the main reasons that linear algebra is more broadly applicable and required for just about any technical discipline is that it lets us solve certain systems of equations. When I say system of equations, I mean you have a list of variables, things you don't know, and a list of equations relating them.
Yeah.
In a lot of situations, those equations can get very complicated. But, if you're lucky, they might take on a certain special form. Within each equation, the only thing happening to each variable is that it's scaled by some constant, and the only thing happening to each of those scaled variables is that they're added to each other. So no exponents or fancy functions or multiplying two variables together, things like that. The typical way to organize this sort of special system of equations is to throw all the variables on the left and put any lingering constants on the right. It's also nice to vertically line up the common variables, and to do that you might need to throw in some zero coefficients whenever the variable doesn't show up in one of the equations. This is called a linear system of equations. You might notice that this looks a lot like matrix vector multiplication. In fact, you can package all of the equations together into a single vector equation where you have the matrix containing all of the constant coefficients and a vector containing all of the variables, and their matrix vector product equals some different constant vector. Let's name that constant matrix A, denote the vector holding the variables with a bold-faced X, and call the constant vector on the right-hand side V. This is more than just a notational trick to get our system of equations written on one line. It sheds light on a pretty cool geometric interpretation for the problem. The matrix A corresponds with some linear transformation, so solving AX equals V means we're looking for a vector x, which, after applying the transformation, lands on V.
Oh, wait.
What's happening here? AX equals V means we're looking for a vector x, which, after applying the transformation, lands on V.
Yes, that's true. We should find the transformation, right?
Think about what's happening here for a moment. You can hold in your head this really complicated idea of multiple variables all intermingling with each other just by thinking about squishing and morphing space and trying to figure out which vector lands on another. Cool, right? To start simple, let's say you have a system with two equations and two unknowns. This means the matrix A is a 2 by 2 matrix, and V and X are each two-dimensional vectors. Now, how we think about the solutions to this equation depends on whether the transformation associated with A squishes all of space into a lower dimension, like a line or a point, or if it leaves everything spanning the full 2 dimensions where it started. In the language of the last video, we subdivide into the cases where A has 0 determinant and the case where A has non-zero determinant. Let's start with the most likely case, where the determinant is non-zero, meaning space does not get squished into a zero area region. In this case, there will always be one and only one vector that lands on V, and you can find it by playing the transformation in reverse. Following where V goes as we rewind the tape like this, you'll find the vector x such that A times x equals V.
Yeah.
When you play the transformation in reverse, it actually corresponds to a separate linear transformation, commonly called the inverse of A, denoted A to the negative 1. For example, if A was a counterclockwise rotation by 90 degrees, then the inverse of A would be a clockwise rotation by 90 degrees.
Oh, that's interesting.
If A was a rightward shear that pushes j hat 1 unit to the right, the inverse of A would be a leftward shear that pushes j hat 1 unit to the left. In general, A inverse is the unique transformation with the property that if you first apply A, then follow it with the transformation A inverse, you end up back where you started. Applying one transformation after another is captured algebraically with matrix multiplication. So the core property of this transformation A inverse is that A inverse times A equals the matrix that corresponds to doing nothing. The transformation that does nothing is called the identity transformation.
Yeah.
It leaves I hat and j hat each where they are, unmoved, so its columns are 1, 0 and 0, 1. Once you find this inverse, which in practice you do with a computer, you can solve your equation by multiplying this inverse matrix by V. And again, what this means geometrically is that you're playing the transformation in reverse and following V. This non-zero determinant case, which for a random choice of matrix is by far the most likely one, corresponds with the idea that if you have 2 unknowns and 2 equations, it's almost certainly the case that there's a single unique solution. This idea also makes sense in higher dimensions, when the number of equations equals the number of unknowns. Again, the system of equations can be translated to the geometric interpretation where you have some transformation A and some vector V, and you're looking for the vector x that lands on V. As long as the transformation A doesn't squish all of space into a lower dimension, meaning its determinant is non-zero, there will be an inverse transformation, A inverse, with the property that if you first do A, then you do A inverse, it's the same as doing nothing. And to solve your equation, you just have to multiply that reverse transformation matrix by the vector V. But when the determinant is 0, and the transformation associated with the system of equations
Well, we have unlimited solutions, right?
squishes space into a smaller dimension, there is no inverse. You cannot unsquish a line to turn it into a plane.
Oh, I mean, there is no solutions.
At least that's not something that a function can do. That would require transforming each individual vector into a whole line full of vectors. But functions can only take a single input to a single output. Similarly, for 3 equations and 3 unknowns, there will be no inverse if the corresponding transformation squishes 3D space onto the plane, or even if it squishes it onto a line or a point. Those all correspond to a determinant of 0, since any region is squished into something with 0 volume. It's still possible that a solution exists even when there is no inverse. It's just that when your transformation squishes space onto, say, a line, you have to be lucky enough that the vector V lives somewhere on that line. You might notice that some of these 0 determinant cases feel a lot more restrictive than others. Given a 3x3 matrix, for example, it seems a lot harder for a solution to exist when it squishes space onto a line compared to when it squishes things onto a plane, even though both of those are 0 determinant. We have some language that's a bit more specific than just saying 0 determinant. When the output of a transformation is a line, meaning it's one-dimensional, we say the transformation has a rank of 1. If all the vectors land on some 2-dimensional plane, we say the transformation has a rank of 2.
Oh.
So the word rank means the number of dimensions in the output of a transformation. For instance, in the case of 2 by 2 matrices, rank 2 is the best that it can be. It means the basis vectors continue to span the full 2 dimensions of space and the determinant is non-zero. But for 3 by 3 matrices, rank 2 means that we've collapsed, but not as much as they would have collapsed for a rank 1 situation. If a 3D transformation has a non-zero determinant and its output fills all of 3D space, it has a rank of 3. This set of all possible outputs for your matrix, whether it's a line, a plane, 3D space, whatever, is called the column space of your matrix. You can probably guess where that name comes from. The columns of your matrix tell you where the basis vectors land. And the span of those transformed basis vectors gives you all possible outputs. In other words, the column space is the span of the columns of your matrix. So a more precise definition of rank would be that it's the number of dimensions in the column space. When this rank is as high as it can be, meaning it equals the number of columns, we call the matrix full rank. Notice, the zero vector will always be included in the column space, since linear transformations must keep the origin fixed in place. For a full rank transformation, the only vector that lands at the origin is the zero vector itself. But for matrices that aren't full rank, which squish to a smaller dimension, you can have a whole bunch of vectors land on zero. If a 2D transformation squishes space onto a line, for example, there is a separate line in a different direction full of vectors that get squished onto the origin. If a 3D transformation squishes space onto a plane, there's also a full line of vectors that land on the origin.
Yeah.
If a 3D transformation squishes all of space onto a line, then there's a whole plane full of vectors that land on the origin. This set of vectors that lands on the origin is called the null space, or the kernel of your matrix. It's the space of all vectors that become null, in the sense that they land on the zero vector.
Oh.
In terms of the linear system of equations, when v happens to be the zero vector, the null space gives you all of the possible solutions to the equation. So that's a very high-level overview of how to think about linear systems of equations geometrically. Each system has some kind of linear transformation associated with it, and when that transformation has an inverse, you can use that inverse to solve your system. Otherwise, the idea of column space lets us understand when a solution even exists, and the idea of a null space helps us to understand what the set of all possible solutions can look like. Again, there's a lot that I haven't covered here, most notably how to compute these things. I also had to limit my scope to examples where the number of equations equals the number of unknowns. But the goal here is not to try to teach everything. It's that you come away with a strong intuition for inverse matrices, column space, and null space, and that those intuitions make any future learning that you do more fruitful. Next video, by popular request, will be a brief footnote about non-square matrices. Then after that, I'm going to give you my take on dot products, and something pretty cool that happens when you view them under the light of linear transformations. See you then.
So that's basically so now we know what a kernel of a matrix like what is like geometrically, right? Then we have the other thing, we have the rank, and it's pretty much the dimensions of the output, right? For what I can understand. And yeah, this is basically what it is. And yeah, when he mentioned this multiplication, I actually remembered that this 2 multiplied by, like this 2 multiplied gives us the identity matrix. So I'm not gonna follow this book completely. I'm gonna, skip forward and try to understand things that might be useful for me. And I will come back later, of course. Like, I want to understand how we can calculate the rank, right? Of a matrix. And then calculate the kernel of a matrix, right? Or a null space. Then I wanna try to learn what vector subspaces are and vector spaces. But before doing this, I want to know how to calculate the inverse of a matrix, right? So next time we will probably do this and try to find a reduced row echelon form. Like, we will search it on YouTube probably, and then we will try to understand all of this. Well, but for now, I'm gonna end the stream, and later we will focus and later we will focus on OpenGL, right? And we will try to learn more about it. But for now, I'm gonna end the stream, and I will see you the next time. See ya.